So today we are going to learn about diffraction. That is, we have observed that under shadow also we can read books. So when we are sitting under a shadow of a tree, we can read the books. So the presence of some light in the shadow region is because of diffraction. The light bends, spreads over the corners or the small openings, and this is what we are going to learn under this heading diffraction. That is the very fundamental aspect of wave nature, diffraction. So the whole diffraction will be studied under the heading of Fresnel diffraction and Fraunhofer diffraction. So first of all, diffraction, it is the spreading of light from sharp corners or when it passes through small openings. This is what diffraction is. The intensity distribution on the screen due to this diffracted light is called diffraction pattern. So this is what diffraction is. Now this whole diffraction will be studied under two heading. Diffraction phenomenon can be studied under two heading. One is Fraunhofer diffraction and the another is Fresnel's diffraction. This is, we will concentrate more here, we will read here. This is in our syllabus and this is beyond our IIT syllabus, IIT and even IP syllabus, Fresnel's diffraction. Now in Fresnel's diffraction, the source, here three things are there in diffraction: source, then screen, and then diffracting element. So here we have three things is important in a diffraction phenomenon: the source of light, the screen where we are going to see the interference pattern, the diffraction pattern, and the diffracting element. I said interference pattern. So there is a doubt that what is the difference between an interference and a diffraction. So there is no technical difference, no basic physics difference between diffraction and interference, just the usage. Generally there are selected things where we use interference and there are selected things where we use diffraction, but basic difference is not there. We will discuss it later on, the difference between interference and diffraction, but technically, basically there is no actual difference. So this is the screen diffraction element. Diffraction element means it can be a obstacle, it can be a opening from where the light is going to diffract or spread out. So in Fresnel's diffraction, suppose this is the screen and this is an obstacle and this is a source. So the light waves, these are rays, the wave fronts are like this. So the light here bends and falls on this screen. So in what we study in Fresnel diffraction, so the source, this obstacle and the screen, when they are at finite distances, then these diffraction studies comes under the heading Fresnel diffraction. So important point, the source, the obstacle, the diffracting element and the screen is at finite distances involved, Fresnel's diffraction. Whereas in Fraunhofer diffraction, distance between these two will be infinite, distance between these two will be infinite. That will be studied under Fraunhofer diffraction, and we are going to study this, not this. This is not in our syllabus. So now let us study Fraunhofer diffraction. Now in Fraunhofer diffraction, this is a small obstacle. Obstacle here is an opening. So you see this is an opening created here, and this is my screen. Here I am going to study the diffraction pattern. Now I place a point source here, but you see my distances is finite, but my Fraunhofer diffraction requires this distance should be infinite. So we have to use a clever technique which we do in laboratory. We place a converging lens and place the source for lens at the focal length of the lens L1. As a result, it produces a plane wavefront. This is my opening, small opening, that is, this is obstacle, this is opening. The light comes out and spreads from this opening. Again this distance is finite, so we place again a converging lens L2 such that this is at a distance F2 from here. So what happens? The light spreads from here. Suppose this light spreads like this. So what happens? So finally they meet somewhere here or anywhere they will meet. That means this is what the diffraction pattern is studied under Fraunhofer diffraction. Again you see this lens L1 produces the plane wavefront and so brings that source to infinity. Again here this lens can focus all these rays on this focal plane, and so this brings screen from infinity to here. This is how we study Fraunhofer diffraction pattern. So now let us study the Fraunhofer diffraction of a single rectangular slit. So we have a rectangular slit. Suppose the slit is like this. This is the opening. I have placed this opening like this. So here this is the opaque element and here there is a transparent, so light will come from this opening and we have a screen here. So when the light spreads, you see light is coming out from this and it is distributed over an area. So what we get some lines along this direction. So the interference pattern, you see this is the intensity profile. If the slit is like this, the intensity profile is like this. So these lines are brightness and darkness. So bands will be like this, and this graph I have shown you, that is the intensity profile, that I will explain later on what is this graph. So this is how interference pattern is going. So to explain it better, I will draw a horizontal slit and I will show how that spreading of light will take place, how bands will be formed here, what is the diffraction pattern formed here, then we will calculate it. So once again I am drawing. Now suppose this is my element and this time I have placed a slit like this. So when the light spreads on the screen, then the spreading is here and the bands will be formed like this. So you see the spreading, this is the terminologies we will use, this distance as A. So the beam spreads along this way, not along this way, the beam spreads along this way. So this is what diffraction pattern is there. Diffraction pattern is there. Now, here we can say one essential difference in the usage of interference and diffraction. While in YDSC or any interference, you see we have two slits S1 and S2 and they serves as 2-point sources. There is only two sources, whereas in the diffraction there are many sources and the whole sources is, you see, distributed over an entire area. So, this is the essential difference where we are going to use when there are 2-point sources, 3-point sources, we say that it is interference taking place, but when the whole sources are distributed over an area and they are going to interfere, we say that there is a diffraction pattern and the diffraction is taking place. So, this is only point sources, this is the area sources. This is what the essential difference between interference and diffraction is. So, diffraction is more fundamental than what we did in our Young's slit experiment. So, now you see this is my slit, it has a width A. The standard terminologies I will use. A is the letter I have reserved to denote slit width and D is the letter I have reserved to tell the distance between the slit and the screen. This is a rectangular slit with dimension A. The width is A, not the length. So, this is the width of that rectangular slit that has A. Now, we wish to calculate the nature of intensity distribution here. So, you see we can do it mathematically. How? So, suppose there is a point P where the waves reach, So, this is one point. Now, what happens when a plane wavefront falls on this slit, then there are many points. I say A1, there is A2, there is A3, A4 ... AN. So, there are n where n is large, tends to infinity. So, there are many points which serves as secondary sources. They emanate wavelets and wavelets from all these sources superimpose here, interfere here to form that interference pattern. So, when the contribution from all these n sources has to be taken, that will decide the intensity as P. So, suppose this wave is there, there is one wave. So, there is many waves and so the wave at P will be denoted as, suppose this is A, capital A sin omega t, A sin omega t, the wave reaching from here at P, then this will have A sin omega t plus theta. The theta is the path difference between them. This is A sin omega t plus 2 theta plus ... finally it will be A sin omega t plus n minus 1 theta. So, if I will add these all harmonic oscillations due to this, then I will get at P. This is how we calculate the resultant wave at this. Now, this is a large mathematical formula and this we are not going to do. We are not going to prove in a mathematical way. We will just justify the some locations of maxima and minima. But actually, if we will carry on, we will have to do in this mathematical way. So, here the important point is that when the plane wavefront is incident on the slit, there are many points which acts as secondary sources and on the screen the contributions from all these points has to be taken. In this way diffraction takes place. Now, this is my slit. Let us first see that what happens at this place. This place is called central maxima. So, you see, suppose there is a A1 point, what we do, we divide the whole slit into two halves. This will be the upper half and this is the lower half. We divide it into a large number of secondary sources. So, equidistant, all the secondary sources are equidistant. Suppose here 10 are there, here also 10. If 20, 20, actually it is infinitely large in number, this is also. So, what happens? You see, there is a wave reaching from, suppose I say A3, there is another A3 means stop here, from here, this is B1, B2, B3. So, suppose this is B3. So, the wave reaching from here A3 and the wave reaching from B3 is in phase. If there is AI, there is a corresponding element in BI, they are equidistant, so the wave reaching here has the same path difference, so they constructive interference. What about A1? You see A1 wave is also going on and there is again a B1. A1 is in phase with B1. So, A1 and B1 there is a constructive interference. A2, B2 constructive interference. A3, B3 there is a constructive interference. So, all the points on the upper half, has a counterpart in the lower half from which they can interfere constructively. Thus, at the center there is a maxima or brightness. So, to prove there is a central maxima, we have divided the whole slit into two portions and we observed that and two portions and all the portions is divided into equally spaced secondary sources. Now, to each point, to each secondary source in the upper half, there is a counterpart in lower half which interfere, which superpose constructively, therefore, you get a maximum. So, the maximum is because of the constructive interference of each one with their counterparts. We see there may be a point A1 and there may be a point AN, they may interfere in a destructive manner. We didn't know, but actually A and A1, B1, A2 and B2, A3 and B3, A4 and B4, so they interfere in a constructive manner. So, there is a net maximum intensity here. So, there is a central maxima. Now, let us locate the position of the first minima. This is a very tricky calculation. First minima, let us see. Now, let us locate where is the first minima. In order to locate first minima, here again the slit is divided into two portions and we have selected a point P where I expect the first minima to be. So, here is a maxima and there is the first minima. So, divide the slit into two portions. So, we divide the slit into two equal halves containing large number of equally spaced secondary point sources. Now, let us consider a point P such that BP minus AP is equal to lambda. Very, very important point. BP minus AP is equal to lambda. This is the point where we are going to study the interference. So, you see what is the path difference? So, if I drop a perpendicular, here this will be a sin theta. This is a sin theta. If it is not clear from this diagram, we will draw a separate diagram. Let us draw separate. This is AB, AB. This is the point source P, and we have assumed this angle is theta. So, since this AB is small and this P is far away, so this angle is also theta. If I drop a perpendicular, this is theta, so this becomes 90 minus theta, so this is theta. So, we won't draw it, so this is theta. So, this is A, so this is A sin theta. So, the path difference, this and this, so the difference of these two gives A sin theta, this distance. So, the path difference which is equal to A sin theta. So, what is the location of P? P is located at sin inverse lambda by A. So, this is the angular position of P. We can write it here. P is at sin theta is equal to lambda by A. This is the angular position of P. So, at this angular position, the path difference between these two waves is this. This is A. Now, suppose I call it this C. The path difference between C, between the waves reaching from C and A is CP minus AP. This is equal to, now the path difference between these two waves will be A by 2 sin theta, which is A sin theta is lambda, so it becomes lambda by 2. This is very important point. The path difference between these two waves is lambda by 2. Again, path difference between these two waves will be also lambda by 2, and the path difference these two is lambda. Now, what we do? We select a point, I call it AI. So, there are many points A1, A2, A3, A4, AN, and here B1, B2, B3, B4. So, this is BI, AI and BI. They are certainly separated by a distance A by 2. The path difference BIP and AIP is equal to again lambda by 2. That means if there are two waves, one reaching from here and one reaching from here is lambda by 2, thus the waves from AI and BI interfere destructively at P. I have a point source called AI, which is at a distance A by 2 from another point source BI, and they interfere at P in a destructive manner. In a similar way, all the points on the upper half, thus all the points on the upper half interferes destructively with their counterparts in lower half. Thus, at P, we are going to have a minima. Hence, at P, we have a minima. The path difference is here lambda by 2 for all the points on the upper half with all the points counterpoints in their lower half. So there is a minima here. So now let us see the position of the first maxima. Here is the central maxima, first maxima. So at P, this is maxima. So this is A and this is B. So now this is the theta. So B at B sin theta is 3 lambda by 2, 3 lambda by 2a. The part difference is 3 lambda by 2. So sin theta is 3 lambda by 2a. In order to get maxima, we divide the slit in 3 parts, 3 equal parts. So these are 3 equal parts, A, B, C, D. So this is A by 3, A by 3, this is again A by 3, this is again A by 3. So what we do, we divide the slit in 3 equal parts, 3 equal parts. Now what we have, we have chosen P such that BP minus AP is 3 lambda by 2. 3 lambda by 2 is the path difference between these two waves. So if I take A and D, so the path difference between DP and AP is, DP minus AP is actually, this is 2A by 3, 2A by 3 sin theta. Already that is 2A by 3 into 3 lambda by 2A. 2A cancels. So this is lambda by 2. So we got DP minus AP is equal to lambda. So this reduces to my previous case. So suppose if I have the path difference between two waves, here lambda, and now you see this is 1/3. So this C is the midpoint of AD. So if these two waves has a path difference, that means as in our previous case, all the points on these will have a counterpoint with a phase difference lambda by 2. So this point has a counter element here with a phase difference lambda by 2. If these two have phase difference lambda, all the points in AC has a counterpoint in CD with which it can interfere destructively. Thus, at P, there is no contribution from the sources of A to D. A to D, no source will contribute at P. They are going to destroy each other. What about DB? So at P, we have only contributions coming from the section DB. So only these sources are involved. They are here, these waves, they are not interfering in a destructive manner. They are incoherently reaching here. So whatever contribution at P you will get, that is the contribution due to BD source. Now what happens? This maxima the maxima at the central, at the first maxima will be contribution due to only dB, whereas in central maxima the contribution is from A to B. So these maxima will be not as bright as the central maxima. So central maxima will be more bright, and thereafter the maximas will be lesser. So this is how to get the location of first minima, first maxima. In a similar manner, other maximas and other minima can be also found by dividing it into 3 times, sometimes 4 number of these, and that can be determined. Now let us see how the intensity distribution on the screen will be. So now let us see the intensity distribution on the screen. The central maxima will be more intense, then other maximas will be less. So this will happen both sides like this. Most of the energy will be within the central maxima. This is the position of sin theta is equal to lambda by A. This is sin theta is equal to lambda by 2A. So the angular position, so angular position means the theta. Suppose this is what angular position theta means. Sin theta is equal to lambda A. So for this you can write theta as theta, this angular position as sin inverse lambda by A. Simply sin inverse lambda by A I am writing. Sin inverse lambda by A. This is sin inverse lambda by 2A. These are the minimas. Sin inverse lambda by 3A. The location of maxima, first maxima we have seen was sin inverse 3 lambda by 2A, and accordingly it will be there. So these are the locations of minima, and the fringes will be uniformly distributed, non-uniformly distributed. In YDAC, all the brightnesses were of the same intensity, but here the brightnesses will be of different. Central maxima will be more bright because it gets contribution from all the sources from upper half and lower half. First maxima gets contribution from 1/3, and these two-thirds will be here a destructive interference. And in a similar manner, the intensity will be, distribution will be symmetric along both. This is how intensity distribution will be dependent on single slit, rectangular slit Fraunhofer diffraction. Now let us consider that if my slit is not a rectangular, but there is a circular opening, and in Fraunhofer experiment, circular opening, then how the intensity distribution will be there. So now let us study the Fraunhofer diffraction for a single circular slit. So suppose this is my diffracting element with a small opening. Again the same arrangement like previous one, by using a lens and all those things we do. What we get on the screen, you see, if this opening is large, then what we get, if there is a wavefront here, then we will get a spot of light. So there will be a bright spot, and everywhere there will be darkness. So that will be at other places will be a shadow region, there will be a white spot. But if this circular opening is very small, we call it pinhole. That means the hole is something created like when a pin is used, then the hole created will be pinhole, that is small in size. Then what we get is here in discs, we get some discs. Disc type image is formed, that is called airy pattern. Airy pattern. So this is what we will get, that this is the interference pattern due to this circular opening. If I draw it, so let us draw another diagram. So this is my slit with a circular opening. You see I have created a circular opening here. Let us exaggerate it. This width is A. This is circular opening, so this is the diameter of the circular opening, and on the screen here we will get a distribution called interference distribution, which we called Airy pattern. This is Airy pattern. Most of the energy is confined within the central maxima. This is the first minima, which in our previous rectangular slit it was actually theta is equal to sine inverse 1.22 lambda by A, which is the calculation is beyond our scope. Simply we have to remember this also theta and this also theta. So this position, that means don't confuse, theta is measured from here, theta is measured from the location of central maxima. This is very important. This theta, the position of the first minima, that is, this is the angular width, angular radius of the central brightness. So you see on the screen, here we will get a bright central brightness. Majority of the light will be within this central brightness. So this is very important, that the angular position of the first minima for the Fraunhofer diffraction for a single circular slit is sine inverse 1.22 lambda by A. Now here again I can redefine my interference with the help of diffraction. You see, in YDAC experiment there were two slits, S1 and S2. S1 and S2 were two slits, and we said that there were two sources, S1 and S2, which sends waves and they interfere on the screen. Now if we are more precise in our treatment of YDAC, we can say that if this is a circular opening, there are superposition of two airy patterns. If these are rectangular openings, then superposition of the diffraction pattern due to rectangular slab. That means interference is the superposition of two diffraction patterns. If we are more precise, we can say interference is the superposition of two diffraction patterns. So this is the most precise treatment of interference. So diffraction is something basic phenomenon, and interference is the result of superposition of diffraction. So this is one more difference between interference and diffraction. So we find that basically there is no technical difference between interference and diffraction than its nomenclature, than its usage. So now we have discussed the Fraunhofer diffraction for a single circular slit. The next we are going to discuss is the resolving power, the limit of resolution, the resolving power of a telescope and a microscope.